Hello everyone, welcome to the module on float glass manufacturing. In this module we will talk a little bit about how the base glass is being manufactured through the process of float glass manufacturing. Before we go into that, a little bit of brief about the glass history. Glass, as everyone knows, is not new. It's been there for ages, for nearly 6 millenniums. Glass was being manufactured for making jewelries 4000 BC, a long time ago. And over the years, it has undergone various transformation, and people have gone into blowing glasses, making hollow glasses. About 300 years ago, they were making glasses flat for the first time by pouring it on a table. And the first continuous process in this process came into being in 1913, the Foucault-Colburn process. And from there, the flat glass is transformed into a float glass manufacturing process in 1957, when this particular process was invented. And as we speak till date, this is a process which is seen as the best quality base glass producer for both architectural as well as for the automotive purposes. The float glass manufacturing process follows this sequence. Okay. First, we need to have the raw materials. We prepare, mix them and convert them into a batch, and we take this batch with various raw material mixed up. It goes into the furnace where it is melted up to a temperature of 1600 degrees centigrade, and when the glass is molten, it's cooled to a workable range where we can give the thickness and the width to the glass, and then it's taken into the float bath, and where the thickness and width is being given, and then we take it into the annealing where the stresses are balanced, and then we take it to the cutting to cut it into the shape and the sizes that the customer demands. The way the glass is being manufactured, a couple of decades ago to how it's being manufactured, you can see a little bit of data at the bottom. The quantum of glass that's manufactured worldwide, and even in India as we speak, the quantity of glass that's being produced is really going up astronomically. This is one good thing, that more and more of glass that we use, the more natural materials that we are using for our architectural as well as various other applications. So the batch area is where the raw materials are received, it's mixed in the right proportion and delivered into the furnace. In the furnace area is where the raw materials are melted, as I said, at a temperature of 1600 degrees centigrade. Which, mind you, it's 1/3 the surface temperature of the sun. And from there it is taken into the float bath, where there is a molten tin bath, on top of which the glass is made float on top of the molten tin. At that time, we equip few equipments like the top roll machines to give it the thickness and the width which we want to meet the customer demands. Once the thickness and the width is given, then we need to cool the glass to room temperature. While doing so, we need to be very, very cautious and careful, because the glass can undergo stress. So the annealing, the slow rate of cooling, is done in the layer, where the cooling is done in different stages before it reaches the cutting line at a temperature of 60 degrees centigrade, when the glass is cut to different dimensions, and then it's stacked and packed and dispatched to the customer's place. Little bit about the raw materials, and I think most of you would know that to make glass we need silica sand. If you melt silica, you will get glass. So the silica is called as the glass former. There are also few other raw materials that we are adding to the silica sand. We will see the need and the purpose behind adding these raw materials in the next couple of slides. Now, as I said, silica sand is the main raw material that is used to make glass. If you melt silica, you get glass. But the problem is, the silica melting point is very high at 1350 degrees centigrade. To melt at such high temperatures, we will be requiring a lot of energy, and on top of that, we need the furnace which can withstand such high temperatures. And to give you another information, nearly 75% of the Earth's crust is made up of silica, And so most of the refractories that we manufacture, that we use in the furnaces, are also made up of silica. How do we melt silica in a silica furnaces? So we need to have a very high temperature withstanding refractories, which is going to make the furnace cost very, very expensive. So for this simple reason, we need to bring down the temperature at which we can melt this silica sand. And for this purpose, we add the flux. Flux in the form of soda ash, sodium carbonate, is added at about 13.5% of the total composition of glass into the sand, which will reduce the melting point. What was 1750 is down below 1600 degrees centigrade. So we wanted to make glass, so we wanted to melt silica. We have a problem of high melting point, so we added the flux in the form of soda ash. Now we were able to melt the silica into glass. But the problem is, the product that we get out of the mix of silica as well as the soda is not stable, which means that it doesn't have the enough strength. Like our bones need calcium, magnesium, etc. The glass also need a lot of strength, and to give the strength, we input calcium oxide, magnesium oxide and alumina, and this will stabilize the glass and give it the required strength. The calcium oxide comes from both dolomite and limestone, and the magnesium oxide comes from dolomite, and alumina, if it is not adequately represented in the raw material, main raw materials, we can supplement with feldspar, which has a high alumina content. So silica, the glass former, to reduce the melting point of silica, the flux we add soda, and to stabilize the glass we add calcium oxide, magnesium oxide and alumina. Now what we want to make glasses in the SiO2 is available in the form of SiO2 itself. The flux, we need it in the form of Na2O, but what we add is in the form of Na2CO3. Na2O goes into the glass, the CO2 escapes into the atmosphere. As a stabilizer, what we need is CaO into the glass, but what we add is limestone and dolomite, which is available as CaCO3. The CaO goes into the glass and CO2 escapes into the chimney. And similarly, MgO is required. Mg we supplement in the form of MgCO3 through dolomite. So MgO goes into the glass and CO2 escapes into the atmosphere. So in fact, for every 100 kg of raw material that we add, only 82.3% of the material gets converted into the glass. The remaining 17.7% goes off as CO2 into the chimney. This process of removal of the CO2 from the raw material is called as the process of refining. Once the raw materials are melted, next the CO2 has to go out, and this refining has to ensure that there is no CO2 in the form of bubbles that's present in the glass is not there anymore. In order to make this refining process much more efficient, we add a refining agent that's in the form of sodium sulfate. So these are the basic raw materials that we use to make different tinted glasses. For example, in the form of green, we need to add iron oxide. To make a blue glass, we need to add iron oxide plus cobalt oxide. In order to make a glass which is bronze in tint, we need to add selenium in addition to iron oxide, and then to make a gray glass, we need to add a nickel oxide. So we add these small colorant components to the main components, which once again I repeat, the glass former silica, and the flux to reduce the melting point soda in the form of soda ash, and to give the stability, the strength required to the glass, CaCO3, MgCO3 and alumina, we add it in the form of limestone, dolomite and feldspar. And then to get this refining process done efficiently, we add the refining agent, which is sodium sulfate. All these raw materials in the right proportion are mixed in what is known as the batch plant. There are big silos which stores this material, and from there it is taken weighed down, and then from there it is taken to a mixer. A bit of water is added to ensure that the batch is at a good 3.5 to 4% moisture content, which will keep the different raw materials homogeneous. The homogeneity of the raw materials is very, very important. To make sure that the glass is optically good in quality, the chemical homogeneity is the most important thing. So, the quality of the glass is largely determined by how good raw material that we put into the furnace and how well we homogeneously mix it. So, batch plant is very crucial to make sure that the final glass quality is the best level that we can aim for. So, from the mixer, it goes into the furnace through what we call as the doghouse. So, this is the schematic which shows the different parts of the furnace, and where the raw material enters into the furnace is called as the doghouse. Typically, the doghouse is something which is there at the entrance of a house, and so this is a place where you feed the raw material, so it's called as a doghouse. And the furnace in itself has got three components to it. The first is the melter, which is the melting and refining taking place. After that is what we call as the neck, and the third segment is called as the working end. And each of the segment has got three parts vertically if you have to take it. One is the tank, which holds the molten glass, and of course we need a roof around, which is called as the crown, and this space between the tank and the crown is called as the superstructure. And we have on both sides, as you can see on the sides, what is called as a regenerator. There's a lot of heat that we need to provide into the furnace to ensure that the glass is melted. And so, in order to retain the furnace at such high temperatures, we need to necessarily let the flue gas go out at a high temperature. In order to regenerate this waste gas at a high temperature going out of the furnace, we have regenerators which puts back the heat back into the system. So, the first is the melter, where the melting happens and the refining happens, and then it goes into the neck. As you can see, then the neck has got a very narrow channel in which, having melted and refined the glass, now we need to thermally homogeneous bring the glass together, and also provide few equipments in the neck, mixing equipment, so that we mix the glass together, thereby the temperature of the glass is more or less homogeneous, which also is essential for the optical quality of glass. So, having melted, refined and homogeneously bringing the glass together, now we need to bring the temperature of the glass to the workable range. So, the end in which we bring the glass to workable range is called as the working end, and then we take the glass into the forming region, which is a float bath at 1100 degrees centigrade. So, some more details of the furnace. Okay, you can see this is how the cross section of the furnace would look like. There are obviously, in order to provide 1600 degrees temperature that we maintain the furnace with, we need a lot of fuel. Most of the furnaces would use natural gas, and for the plants which do not have the facility for natural gas, also uses heavy oil. So, there is a burners set up on both the sides, as you can see in this diagram. In addition to the heavy oil or the gas, we can also supplement energy through electrodes from the bottom. So, this is quite efficient, the electrodes, if we make tinted glass, for example, because the bottom temperature tends to go too low because of the heat transfer being restricted due to the non-availability of radiation as a source of heat transfer. The electrodes from the bottom can really help in quickly providing the heat into the molten glass from the bottom. We will come to that later. For now, this particular picture shows us how the fuel is being injected. In this case, we call it as the right side, as in the picture we can see, and the flame is coming out from the right side. The oxygen that is required for this combustion comes through the regenerator. The red color, the blocks that you see on both sides, the oxygen in the form of combustion air comes through the regenerator on the right side and comes over where the oil is being injected into the furnace. The combustion takes place. The ignition temperature is already available because the furnace is always maintained at 1600 degrees centigrade. So, from the right hand side firing, With the heat going into the glass, the waste gas goes out of the furnace through the left hand side regenerators. When it goes out, the temperature of the flue gas is around 1450 degrees centigrade. In order to maintain this temperature at 1600 inside the furnace, there is no other way but to let the flue gas go out at 1450 degrees centigrade. This flue gas, when it goes out through the regenerators on the left hand side, the regenerator is stacked up with special refractories which can quickly absorb the heat, quick heat transfer capacity, and also got a very high area, surface area to volume ratio, so that it has a lot of surface area for it to take the heat of the flue gas that is going out. So when the flue gas comes out, this refractories absorb the heat, and what comes in the waste gas at 1450 degrees centigrade, when it goes out into the chimney, we let it at 450 degrees centigrade. These regenerators continue to absorb the heat, but it has been designed in such a way that it can absorb the heat for about 20 minutes time, not more. So what we do is to do a process called as a reversal.